Today we are going to talk about Higgs boson physics. I would encourage you to basically interrupt me in between if something is not clear or I make certain statements which you don't agree with, so that I can clarify or I can get corrected. So what we are going to actually talk about is this particle Higgs boson. If you go to the PDG and you try to collect information about this guy, what you would learn that is the only fundamental scalar, fundamental in the sense that whatever we know so far in the particle spectrum of the standard model, which does not have any electric charge. It is actually neutral under color. It's a spin zero with the CP even property. And its measured mass currently is about 125. We don't have like exactly measured width, but there is an upper bound from the experimental data that we have. And the particle was discovered in 2012, and since then, people are trying to understand or characterize this particle as much as possible. Because once you know the mass of this particle, there are a lot of predictions from the standard model side, and you would like to verify those predictions before confirming that it is indeed the standard model Higgs boson or something else beyond the standard model. So yesterday, Fabio gave you a review. I'll just basically describe the same thing in just one page. That what we are actually, when we talk about the Higgs, we are talking about this electroweak sector of the standard model, which is described by SU2L cross U1Y gauge symmetry. And the fact that the gauge bosons or the mediators of the electroweak interaction, they are massive, that tells that the electroweak symmetry is broken in nature. So how do we actually do that? In the standard model, this the breaking of the electroweak symmetry is realized with the help of SU2 doublet, which is like 4 real scalar fields sitting here in this doublet, SU2L doublet. And the complete Higgs sector can be described by this Lagrangian, where you have the kinetic term, you have the Yukawa term, and you have the Higgs potential. So depending upon like what is the nature of these parameters mu and lambda, as all of you know, that we can give a non-zero vacuum expectation value to this Higgs field. So the moment actually you give the non-zero vacuum expectation value, we can actually give masses to the gauge bosons, mainly W and Z. And luckily, this doublet is sufficient to generate the masses for the fermions as well. And as a result of, so the Higgs field is nothing but the fluctuation over this vacuum, which is this symmetry is broken around 246 GeV that we learn from the muon decay. And this basically, these terms, once we replace phi by V plus H, this is going to give us the mass of the Higgs boson and all the couplings of the Higgs with the gauge bosons as well as with the fermions. So let's look at what are the couplings that we have for the Higgs. So there are basically Higgs coupling with the fermions, with the gauge boson, and with itself. So they are trilinear couplings and quartic couplings. And as mentioned yesterday, the quartic couplings are related to the trilinear coupling. So these couplings of Higgs with the fermions and gauge boson, they are proportional to their masses, and the mass dependence is linear for fermions and quadratic for the gauge bosons. So the next question would be, since we know the mass of the Higgs boson, what do we know actually about these couplings? How far from the experimental data? And this plot was shown yesterday also, that we pretty much know the couplings of Higgs boson with the gauge bosons and heavy fermions with an accuracy of 10 to 20%. But its coupling with the light fermions and its self-coupling is practically not constrained. So we need to still learn about the Higgs potential. So about the Higgs self-coupling, I will talk later. Let's first actually get into the details of the Higgs. So what are the actually modes through which Higgs can be produced? So there are mainly 4 modes in which Higgs can be produced. The dominant one is the gluon-gluon fusion mode, which is a loop-induced production mode for the Higgs. Then there is a vector boson fusion mode that can also, where Higgs couples with the mediating electroweak gauge bosons. Then we have Higgs-Strelung process, where Higgs is produced in association with a vector boson. And then we have Higgs produced in association with TT bar. And there are some other processes which have less cross section. For example, here one such process is the production of Higgs in association with a single top. This process is important, but I will talk about this process more tomorrow in my lecture on top physics. So as you can see, this plot tells us what are the rates for these Higgs production processes. The single Higgs via gluon fusion, it tops the chart. The cross section is maximum for this. Then that is actually followed by the vector boson fusion. Then the Higgs-Stirling process. Then there is a small component BB bar Higgs, because if TT bar Higgs is there, you can expect BB bar Higgs to be also there, because that coupling is small, but it's not zero. And there is actually single top Higgs production in the single top as well. These are just basically a summary that how well do we know these cross section from the theory side, and we will talk about it now. So single Higgs production, where you produce one Higgs and in the initial state you have gluons. Since Higgs is not charged under color, so therefore they cannot connect directly, and therefore the only guy who can talk to both of them is the heavy quark, because the light quarks have very small Yukawa coupling, so you can ignore them. Is mainly this process is mediated by the top quark. Now, just demanding actually Lorentz covariance, you can write down this amplitude for glue to Higgs, which has two Lorentz invariant factors, B00, B11. We do not need to know about them at this stage. But what is important, you will see that if you demand the gauge invariance with respect to these two gluons and apply the on-shell condition for the gluons, you would learn that these two are related. Okay? And therefore, all you need to know that what this B00 is. So this expression is actually very general in the sense that this is true for leading order. Then you can actually go on doing higher order virtual correction to this process, and this expression remains true. All you need to know that what this m mu nu is, whether it's one loop effect, two loop effect, three loop effect. In this way, B00 has a perturbative expansion in QCD coupling or electroweak coupling, whichever corrections you are talking about. So at leading order, we know what is the result. The result is basically written in terms of the heavy quark mass in the loop, and one loop actually function which is known as a scalar integral. Okay? There are three propagators. So you can associate all these three propagators to these three internal lines. So you can actually clearly see that this expression at leading order is finite. Although this process is loop induced, this process is finite, and it is expected because if there was any, suppose that it was actually not finite, then you would have expected in your theory a counter term which would connect the gluons and the Higgs directly. Since such a counter term is not there, you should expect that when you calculate this loop, you get finite answer. And C0, as you can see from the dimensional analysis also, it's ultraviolet finite. So at leading order, what we have, the result depends upon the mass of the heavy quark in the loop and the mass of the Higgs boson. It has a very nice property that if you take the MQ to infinite, then this amplitude becomes independent of the mass of the quark or mass of the fermion in the loop. So usually, basically, we in theories, for example, if you have any heavy degrees of freedom in QCD or QED, if you take that heavy degree of freedom to infinity, it actually decouples, meaning any amplitude depending upon that degree of freedom would simply vanish. But this does not happen here, because this theory is broken. So this theory, since it is the part of the electroweak sector, and the Higgs is a result of electroweak symmetry breaking, all the masses are related to the vacuum expectation value where the symmetry is broken. You do not expect this decoupling to take place in the electroweak sector, and this is what is happening, that you get a non-zero result. So effectively, what you have done, you have taken this loop, the mass of this loop to the infinity, so it has shrunk to a point. Okay? So you have come across, by taking this limit, an effective gluon-gluon Higgs vertex. Okay? So this feature can be utilized to probe if you have any heavy quarks beyond actually top quark, which is part of, say, some BSM models, then you expect the same feature to be present for that quark as well. So meaning that if it's very heavy, it should actually contribute to, effectively, it should contribute to the production cross-section of gluon to Higgs. So this has been actually utilized, in fact, to rule out many models of new physics, which have, like, say, fourth generation of quarks. So instead of basically focusing on that vertex that we got by taking the quark mass limit to infinity, you can basically look at this effective Lagrangian, which is between the gluons and the Higgs, and we can derive the same effective gluon Higgs vertex from this Lagrangian. But we get actually more, and that more is basically that you also get Higgs coupling with not only with the 2 gluons, but with 3 gluons and 4 gluons. So I will encourage you to take this Lagrangian and derive all the Feynman rules. The results are available in the literature also. And if you need any help, let us know. We can actually help you with that. So why do we need this limit? We need this limit because it provides a great simplification if you want to perform higher order calculations. So if this limit is actually good, then what does it mean? That if you want to predict the glue to Higgs cross-section more precisely, you would like to perform higher order corrections. Now, glue to Higgs is already one loop effect. If you want to perform higher order corrections, you need to go 2 loop, 3 loop, and so on. Okay? But in this theory, in Higgs effective theory, your one loop effect becomes actually a tree level. One loop diagram is effectively a tree level diagram, while a 2 loop correction would correspond to effectively a 1 loop diagram. So this is a simplification, although we need to worry about whether this simplification is actually valid or not. You would like to basically, if you can perform computation exactly, and in this HEFT, you would like to definitely compare whether these two calculations, they agree or not. So for example, here basically I'm showing you a plot where the next to leading order calculation for glue to Higgs has been performed exactly, as well as in HEFT. And as you can see, at the level of total cross-section or inclusive cross-section, the agreement is very impressive. Okay? But this need not be the case because it depends that which observable you are interested in. And so you need to actually worry about this limit, whether it always works or not. So just for your information, or probably you already know, it doesn't actually always work. So one of the objectives of higher order correction is that if you perform higher order corrections, since all our predictions are of perturbative nature, because of this there is a scale dependence. For example, renormalization is scale dependence. So if you go on actually computing higher order correction, your scale variation becomes smaller and smaller, so your predictions are more precise. In this case, in most of the cases, QCD corrections, your cross-section also increases when you include higher order terms in your perturbation theory. But what is actually more important, that your predictions, they become actually more precise. For example, as you can see here, here is the variation, scale variation for the leading order, while when you go to next to leading order, and then next to leading order, and next to leading order, your scale variation, this variation becomes almost actually flat, which tells you that your prediction is not now actually more precise. And if your experimental observation is precise enough, then you can now look for any discrepancy or agreement accordingly. So since at the leading order, we don't have, it's a 2-to-1 process. So the Higgs does not have any transverse momentum. But once you include the higher order correction to it, you start adding actually more jets. And this addition of more jets leads to the PT distribution or PT of the Higgs. So for example, here you are seeing the PT distribution of Higgs at leading order, which is effectively is an NLO effect, and NLO and next to leading order NLO. So this LO is connected to the NLO here, NLO is connected to this, and NNLO is connected to this prediction. Is that clear? Okay, good. So more about actually higher order corrections, Shaw will talk tomorrow. I will proceed from here. So with all this state-of-the-art calculation, the most updated result that we have for the Higgs cross-section, inclusive cross-section, at 13 TeV LSC for Higgs mass of 125 GeV is something about like 50 picobarn. Okay, and there is a theoretical uncertainty on top of it, which is in the range of 5 to 6%. And here is a decomposition of various effects which contribute to this number. So for example, leading order cross-section is about 16 picobarn, and then once you include the next to leading order cross-section, it's actually higher than the leading order corrections. So in QCD, this is not unusual. You may get higher order corrections which are larger than the, say, leading order corrections, and that is due to, mainly in this case, this is due to the color factor. So, so currently, actually, on the QCD side, these corrections are known at the level of NQ below, and at the level of Electroweak at the level of Electroweak, they are known at the NLO level, which adds like your cross section to 5% more. Okay, let's move to the second production channel, which is the vector boson fusion. So as I said, basically in this, what is exactly happening, that you have these two quarks which radiate the vector bosons, and then they fuse to produce the Higgs boson. Okay, so this is the vector boson fusion is here. So this process has a characteristic feature that in your detector you are going to basically find these jets in the forward and backward regions of your detector. So because you can expect Higgs plus 2 jet coming from other production modes, for example, there is a gluon-induced process which produces Higgs plus 2 jet, and then this process of Higgs-Strömling, which we will talk after this, that also leads to the same final state when the vector boson decays hadronically. So you can actually use this feature to distinguish the vector boson fusion production channel from other production channels leading to the same final state. And the other interesting property is that since this part is led by the electroweak vector bosons, which are color singlet, so you do not actually expect any QCD activity in the central rapidity region. So by studying this process, we also can constrain the coupling of the Higgs with the gauge boson. And at present, actually, we know these calculations at the level of next to leading order in QCD and NLO in electroweak. You have a question?
So why the jets are in the forward and backward region? Back to that.
Why they are?
Why?
So you imagine basically that you have these two protons, right? These quarks are coming from these two protons, and they radiate this electroweak bosons, W and Z, okay? So they don't actually get a very hard kick, so they actually remain along the beam line. So one of them you will find in the forward, the other in the backward direction. So on the right hand side, I'm just showing you the PT distribution of the Higgs, which is already present at the leading order. And you see that the corrections here, they are actually negative. So the leading order cross section is larger than the next to leading order corrections. So this is something unique to the vector boson fusion process. Okay, moving to the Higgs-Strömling process. This is, if you have studied the de Leon process, this is exactly like that quark and antiquark, they produce W and Z, and then this W and Z radiates a Higgs boson. Okay, this process is important from the point of view that this has been used to detect the Higgs decay mode into BB bar when the PT of the Higgs is very large. In the boosted region, you can use this channel to study Higgs to BB bar decay mode. Here on the right hand side, you see the QCD and the electroweak corrections, and in this case, the electroweak corrections are negative while the QCD corrections are positive. So when we talk about this next to leading order correction, then there is additional contribution which comes for the case of Higgs plus Z. There is an additional contribution which appears at next to leading order, but that is not actually quark anti-quark induced, but it is glue induced. So if you consider like glue to Z plus Higgs, it's a box diagram which also contributes at next to leading order. So in these predictions, that has been also included. So finally, the Higgs production in association with TT bar. The importance of this process is that this directly couples with the top quark. So unlike glue to Higgs, where the Yukawa coupling is part of the loop, here the TT bar Higgs coupling is part of the tree level coupling. Okay. So this channel, if we observe this channel, we study this channel, we can obtain the information on the top Yukawa coupling. We become directly sensitive to the top Yukawa coupling by studying this. The effect of QCD correction in these processes, they increase the cross section by 20%. The electroweak corrections are also known in this case. And here is the recent data from CMS, where both the Atlas and CMS recently, they had observed the TT bar Higgs production channel as well. So for quite some time, we knew the glue Higgs, the VBF and the VH, but TT bar Higgs was missing. But now we have observed this channel as well, which combines the data from 7 TV, 8 TV, and 13 TV runs. So here's the summary of all the single Higgs production cross sections. So as you can see, for different collider energies, these cross sections are tabulated for Higgs mass of 125 GeV, and you can now we can ask basically that, okay, this is the theoretical prediction. What do we know about these predictions on the experimental side? So one quantity which can tell you this information is what is known as signal strength. Signal strength in this case is nothing but the your measured cross section divided by the cross section from your theory side. In this case, the theory is the standard model. So if your data is matching with the experimental prediction, then you expect the signal strength to be 1, right? So this is what basically in plot you see that this line here, okay, we have like the signal strength for the gluon fusion channel and all the other production channels. And here is the line 1, which is the standard model line, and the data with the 1 sigma and 2 sigma uncertainty, which is consistent with the standard model prediction. The objective of the future runs would be to minimize these error bars and see if there is any discrepancy, because for some of the data points, the central value is away from this line 1. Okay.
So in the first line, for the Taylor the previous cross section is smaller than the WS CH channel. In other channels, this is greater than. Why is that happening?
I don't know the answer. Can someone tell? So the Tevatron, actually, why the in what sense actually PDF? Is it so? The question is basically that at the Tevatron, why VBF cross section is smaller than the VH cross section. So the okay. In the case of WH, you will have, yeah. So what is the question?
No, factor 2 and the WH. So that's same order.
You expect them to be of the same order?
Which one?
WH
and EVF.
These two. See, the difference is again like we can, like the fact that YWH is actually larger than ZH, we can again basically attribute it to the PDF, because this time we have like Q and Q prime.
No,
Right. Oh, but and this includes basically both W plus H and W minus H. Okay. Yeah.
It's more like VH is smaller than VHC, because this we needed the C form.
Okay. Okay. So since we have actually learned about the production, we would like to know, is there a question? Okay. So if you want to basically interpret the data from your experiment, you not need to know only the production part, but also decay. That what are the decay modes for the Higgs boson, because it's heavy, and we have already seen it couples with the fermions and the gauge bosons. So here basically there is a plot where you can see the branching ratios for the Higgs in different decay modes, depending upon what is the mass of the Higgs boson. So before the discovery of the Higgs boson, you basically you had some expectation that where its mass can lie. So from here the range is taken from 80 to 200. And what we are now today interested in is mass of the Higgs boson around 125 GeV, where you can clearly see that the dominant decay mode is the BB bar decay mode, followed by WW, ZZ, and all that. And here is the theoretical prediction from the standard model side, taking the mass of the Higgs boson at 125 GeV. So let's first see the Higgs decay into the fermions. So kinematically, the only allowed decay modes are, except basically top quark, can decay to all the fermions. But its decay, since the coupling is proportional to the mass, it is actually suppressed by the fermion mass. So from that point of view, the largest decay mode among all the fermionic decay modes is the BB bar, followed by tau plus tau minus and CC bar. And we know actually this decay prediction with an accuracy of N4 LO in QCD and NLO in Electroweak. What about actually gauge bosons? So Higgs couples with the gauge bosons, but it cannot decay into heavy gauge bosons, keeping both of them on shell. So what it suggests that one of the gauge bosons has to be always off shell. So there are actually, what are the decay modes? So W can decay into, so leptonic modes are like the best modes to observe Higgs boson because of the less background. So so if you consider basically the decay mode where in the final state you have 2 leptons and 2 neutrinos, and therefore then in that case you have to consider the interference between WW star and ZZ star modes. And because Z can decay into neutrinos, so in the standard model itself, you have a small invisible decay, partial decay width for the Higgs. The best final state in which we should actually look for the Higgs boson is the charged lepton channels, and there are 3 possibilities: 2 electron, 2 muon, 4 electron, and 4 muon. This is a very clean channel because the background is very less, though the rates for this decay is small. But you can actually reconstruct the Higgs mass completely, and that's how basically Higgs was actually discovered. So this is one of the discovery modes where you can reconstruct the Higgs mass. In this plot, you can see this is the 4 lepton invariant mass, which peaks around 125 GeV. There's the Higgs mass. The rest is actually background here. It has actually this channel is not only useful for determining the mass of the Higgs boson, it also basically can characterize the Higgs in the sense that you can utilize this channel to study the spin and CP properties of the Higgs boson. And this is possible because this Higgs decays into 4 particles. So since there are actually 4 particles, so unlike those decay modes where you have only 2 particles, such final states, they have non-trivial kinematics. And you can, that means basically you can use these kinematic, say their momenta to construct observables which are sensitive to the spin and CP properties. So in this plot, what you see that there are actually 2 possibilities has been displayed because spin 1, since Higgs decays into 2 photon, spin 1 is actually already ruled out. So the other 2 possibilities are spin 0 and spin 2. And the data actually suggests that the spin property of this particle is consistent with the spin 0, which is the blue shaded region with 1 sigma, 2 sigma, and 3 sigma accuracy, while the red ones are the spin 2 cases. Okay? So as I said, basically, since you have many more particles in the final state, you can construct observables. For example, one of the useful observable is a phi, which is the angle between the decay planes of the two Z bosons. If you study this observable, then this can tell you whether, if you already know that this particle is a spin 0 particle, by studying this distribution, you know if it is a CP even, then you are supposed to basically get this, the curve with the red dots. And if it is actually CP odd, then you are expected to basically find this distribution. So that's because of this usefulness of this channel. This is also known as golden channel of Higgs decay. The other channel which is very important, very clean, is the Higgs decay into 2 photons. So like the Higgs production in the gluon fusion, this decay mode is also loop induced. So as you can see, this decay receives contribution from heavy fermions, like in the case of production. And there are actually double loop mediated diagrams as well. Okay? Once again, you expect these contributions to be finite. So this contribution is dominated by the double loop, and there is a destructive interference between the fermion loop and the bosonic loop contributions. And if you take the fermion or the gauge boson mass to infinity, once again you will find that there is no decoupling. In the sense, you find basically a finite result. So as I said, this channel is very clean because there is very less background for the photon. All you need to do, collect your photons and plot the invariant mass, and your signal is expected to come out like a bump here at 125 GeV. So this was also this channel is also a discovery mode. Like Higgs decay into 2 photons, Higgs can also decay into Z photon, but its rate is actually very small, and still we haven't actually seen this decay mode yet. So here is the summary. Like we saw in the case of production, in the case of decay, we can again talk about a signal strength, which is nothing but the ratio of the branching ratio. So your observed branching ratio and the calculated branching ratio from the standard model side, you should again expect if there is the observation is consistent with the prediction, then all these lines should be actually consistent with this line at 1. Okay, and this is what the case is. But once again, as I said, these are consistent with some accuracy, which is like say 1 sigma and 2 sigma. The central value is still away from this line. The hope is that as you collect more and more data, the central line actually pushes towards the this line. So we can ask that since we have 2 channels which can help us to determine the mass of the Higgs boson, the Higgs to 4 lepton and Higgs to photon, CMS and Atlas basically they have studied and measured the mass of the Higgs boson, and currently the measured mass is something like 125.09. That's the best width from. This is from the run 1. This is probably updated after combining the run 2 as well. What about the Higgs width? So the width, if you calculate for 125 GeV, depending upon, like, since we have all the information about the coupling and the mass, that is very narrow width, about 4 MeV, with theoretical uncertainty in the range 4 to about 4%. But since this width is nothing but if you have access to all the partial decay widths, you just want to basically sum them to obtain this width. But still we don't have any information. What we have is basically an upper bound on this total decay width from the experimental side. So there are some actually theoretical proposal that how can we we can try to basically measure these widths in one shot. And like one example is here, for example, if we consider the diphoton in the gluon fusion channel, then you have two contributions. One is basically where glue goes to Higgs, and then Higgs decays into two photons. So there are two one-loop triangle diagrams connected by the Higgs propagator. And then there is also same final state is generated by a box diagram, which is induced by the glue, right? So glue, there is a quark loop diagram, and there are two photons. So the interference of these two diagrams, that is basically shown to be sensitive to the width of the Higgs boson. And this effect is at the level of actually 2%. So here in this plot, what has been shown that if there is no interference, then at the resonance, where S hat equals mh squared, you get this shape. While the interference effect, basically that is a destructive interference, and you get this gray line in that case. So by making the measurement here, very precise measurement can give us information on the total Higgs decay width. So since we are done with the single Higgs production, let's talk about the double Higgs production. Double Higgs production, all you have to do, if you know all the single Higgs production modes, just add one Higgs wherever you can add, okay? And that gives you basically, once again, these four channels, two Higgs production in the gluon fusion, then VBF, then Higgs-Stralung, and the TT bar, and the Higgs production, double Higgs production in association with TT bar, okay? It's just basically you add. The importance of studying double Higgs production is that this is directly sensitive to the trilinear coupling, which you are interested in knowing, because then only you would know whether the Higgs, the potential which is responsible for the electroweak symmetry breaking is indeed the Higgs potential that is in the standard model. So here's the cross-section, relative cross-sections of all these processes. Once again, because of the large gluon flux of the luminosity, the double Higgs production via gluon fusion is the largest. And on the left-hand side here, you see the variation of different channels with respect to the trilinear coupling. So there is a large sensitivity, especially for processes glue to Higgs-6 and TT bar Higgs-6 on the trilinear coupling. If you vary, then the cross-section actually varies a lot, okay? So this double Higgs production via gluon fusion, as you can see, there are like box diagrams and the triangle diagrams. Once again, there is a destructive interference effect playing a role, and that one needs to actually be careful or be aware of. Right now, actually, the best calculation for the double Higgs, that is basically a numerical computation at next to leading order. So leading order prediction, for example, at 13, 14 TeV is about 20 femtobarn. Okay, this is very small. And the next to leading order basically gives rise to 70% more contribution. And here on the left hand, on the below is the distribution mass, the invariant mass distribution for the Higgs. All the corrections beyond the leading order, they are centered around the distribution where it peaks, which is the TT bar threshold in this case. Okay, so I will quickly just talk about this Higgs self-coupling, because I said that in this standard model, you expect as a result of electroweak symmetry breaking to come across these two types of couplings, the trilinear and the quartic. Okay? And in the standard model tells that if I know the mass of the Higgs boson and the wave, then I know everything. In this case, these two couplings are correlated to this parameter lambda. And the value of this parameter in this standard model is 0.13. But the question is, unless you basically measure this, you don't know whether this is indeed the standard model Higgs or not. Okay? So because there is a possibility that your Higgs potential is, has BSM effects. Okay? In that case, there will be additional terms, and those additional terms are expected to modify this value. Okay? In principle, the effect can be such that the lambda 3 and lambda 4, they are no more correlated. And it is indeed possible. You can just imagine adding, say, some dimension, higher dimensional operators, say dimension 6 and dimension 8, and you can show, as I will show in a while, that the lambda 3 and lambda 4, they are no more correlated if higher order effects to be parameterized by higher dimension operators of dimension 6 and dimension 8. Just one example. So as I said, basically what is the problem? Like if we want to measure these couplings, the problem is that the channels, the dominant channels, which are sensitive to these couplings, their rates are actually very small. So for example, single Higgs production is like 50 picobarn, while if you compare the double Higgs and the triple Higgs, their cross sections is super small, and this is at the inclusive level. If you want to observe these channels, you need to consider some Higgs decaying into some final state particles. So that reduces the cross section actually further, and this is one of the reasons that why we haven't actually observed this process at the LHC. What we know that with the data, all we know that there is an upper bound on the cross section, that the cross section cannot be larger than this, which implies that we can place some limits which are very loose. Practically, they are not limits. What you expect, this scale factor, which is the ratio of the lambda 3, the measured one divided by the standard model one. If the observation is consistent with the standard model, you expect this kappa lambda to be 1, right? But what we know today is that kappa lambda is somewhere between -5 and 12. So just imagine that you expect, if a standard model is indeed the correct theory, then kappa lambda should have been 1. But right now, actually, we are not very sensitive. So there are actually some future projections which tells us that we can do better and rule out the values of kappa lambda, which is smaller than 0.8 minus on the negative side, and larger than 7.7. Okay, so what to do in that situation? Of course, you can actually wait for more data and try to analyze and hope that one day we will see the double Higgs process, and we can basically try to obtain the limits on kappa lambda. But meanwhile, what you can do, you can try to basically ask different questions. Is there other ways to become sensitive to the Higgs self-coupling? So for example, single Higgs, we already have data on single Higgs. We can ask this question that if we consider higher order effects in single Higgs, meaning what you are trying to say that you know theoretical predictions with the QCD, if you include the Electroweak corrections also improve your prediction for the cross section, then you would be in principle sensitive to the trilinear coupling. So for example, this is one of the contribution which would appear in the Electroweak corrections of the single Higgs production, and here is in the decay. So yeah, I had started a bit late, but yeah, okay, fine. Okay, so what does it mean? Basically, effectively, this correction that can be written this way, that this is any of your observable, be it total cross section or distribution, and you calculate this at next to leading order, which is related to this kappa 3 or kappa lambda. They are same for us. All we need to know, if kappa 3 is in the standard model, then kappa 3 would be 1 in the standard model case, and if you have a BSM, in that case, all you need to do, you need to just actually vary kappa 3 to obtain the prediction for the cross section or the distribution in the BSM. So we did that exercise because using the single Higgs data and using this observable, we have fit it, and what we have found that at 13 TeV, we are already basically sensitive to kappa 3 at the level of like -4.7 and 12.6. Again, it's very loose, but remember this is with the 13 TeV data. Okay. Here on the right hand side, what we are seeing that what is the like how different production channels they are able to constrain the trilinear coupling. So for example, on the negative side, the TT bar Higgs channel is the best channel to constrain trilinear coupling, while on the right hand side, for the positive values of kappa lambda, they get well constrained by the gluon fusion production channel.
What is the error?
Sorry? Oh, these are actually, these are actually, okay, so let me just say something. So for example, if you look at the green, this just consider on the TT bar Higgs, okay? So here we have actually one line which is a solid line, and there is basically another which is a bit fuzzy. That is, so what we are doing basically in the fit, we are using the total cross-section information in here, in this case. And in the other case, we are using a distribution, in this case, the PT distribution of the Higgs, while performing the fit. And the band on these, they are related to the uncertainty which is in the data that we have actually used. Yes. In this case, it's a statistical. Okay, so what we did basically, that was followed up by the CMS collaboration, and probably, if I remember, the Atlas collaboration has also performed this analysis. So the tools that we developed, the CMS basically performed the analysis in the single top and TT bar Higgs channel, and they have obtained a limit which is very close to our analysis, which was very simplified, but they have done a more robust analysis and finding the range for allowed range for the kappa lambda, which is close to what we have found. Now you can ask this question, okay, so far so good, trilinear coupling, you have basically an alternate way, although it's you can call it basically a complementary information, because it's not giving you something more robust constraint compared to the double Higgs. So you would like to know what happens basically for the quartic coupling. Should we go for producing triple Higgs at some future collider, or we can extend this technology to double Higgs and obtain some information on the quartic coupling? Yes?
Why is the upper limit loose on positive side of kappa lambda?
Right. So remember, actually, I showed you one plot, which is here. Okay. So this is the so when we increase the value of kappa lambda, the cross section actually goes down, the total cross section. So this is a gluon fusion channel. Okay. So what is happening basically, that since your cross section is actually very small, therefore you get basically the constraint actually becomes actually less tight compared to the negative side, where it grows when your kappa lambda grows on the negative side. Okay, so it's related to this effect which we have here. Okay, so this is what actually we also did, that let's actually try extending that idea to the double Higgs production and become sensitive to the quartic coupling. Okay, so I'll not actually get into much more details, but I will just actually emphasize that the only difference compared to the single Higgs case is that in the single Higgs case, your trilinear coupling was the leading effect. So you could basically just take that BSM effect as a scale factor. In this case, you already have the trilinear coupling, okay, in the triangle diagram. And if you want to consider the next to NLO electroweak, you need to do it actually systematically, because both in the standard model they are correlated. And the one way basically to do it systematically is that you add gauge invariant higher dimensional operators. And this is what I said, that if you do that, then you can see that your lambda 3 and lambda 4, they are related to two Wilson coefficients C8 and C6 and C8, which are the Wilson coefficient of 6 dimension and the 8 dimension operators. Okay, so if you do that, basically your calculation becomes it's bound to be actually gauge invariant. And now you have actually a modified observable. In this case, we are calling it like phenomenological cross section. So you have the leading order double Higgs production, which receives corrections from these two loop contributions. Okay. So these contributions are listed here. So these are basically just at the one loop level, you already are sensitive to the C6, but at two loop level, you become sensitive to the C6 and C8, which effectively means at two loop level, you are sensitive to the trilinear as well as quartic coupling. And that's the basically main goal of this calculation, that we want to get first information on the quartic coupling. These are the sort of actually diagrams which we will worry about if you have to systematically compute these corrections. And here is the effect of those corrections in terms of like numbers at 14 TeV, at 100 TeV. So at the leading order, the C6 contributions, they are like what, they are quite large. If, in fact, if C6 if it's very small, then the cross section is basically governed by the leading order prediction itself. So the common feature is that as you grow higher and higher energy, these corrections basically, the total cross section basically increases depending upon what is the relative contribution from these two loop and one loop corrections. The same effect is being displayed at the distribution level, because here the fit we perform, we will be using the information on the invariant mass distribution for the Higgs, for the double Higgs. And here is basically my last slide, where I'm just showing that all we have done, we have, after having these two loop corrections included, you will have modified prediction for the invariant mass distribution. You just perform actually chi-square analysis, which now depends upon parameters C6 and C8, or trilinear and the Quartic couplings. And this is basically the result. As you can see, they are C6 and C8, they are actually very much correlated. This is the result from the double Higgs. The only problem is that at 14 TeV, you will not be actually sensitive. So this effect you expect to gain at 100 TeV collider. You need to build a new collider if you want to gain information on the Quartic coupling from the double Higgs channel. But then you can ask that at that collider, basically, I would like to know that what is the capability or sensitivity in the triple Higgs production channel. So that result is actually here. So here we have the combined result. This line is nothing but actually this region is this region. So from the double Higgs, and these two regions are from the triple Higgs production, depending upon what is your tagging efficiency for the B quark, which is coming out of the decay of the Higgs in the final state. So in short, suppose that I find that my trilinear coupling is consistent with the standard model value, then this analysis basically tells that from the triple Higgs in a certain decay mode, we will be sensitive in this range to kappa 4 will be constrained in the range -6 to 18, while this analysis which we have done based on the two loop corrections in double Higgs, that would be something like -4.2 to 6.7. Okay, so.
I think the direct search numbers may be better, because what has been, now there are several channels that have been analyzed.
Probably.
This one plus the 4v2 clocks and the 6 weeks.
Okay.
All of them are reaching 2 sigma in the standard model.
I see.
And since they are independent, in principle, we could combine them and then maybe get
It's in double Higgs, you mean?
triple Higgs.
Oh, triple Higgs.
Yeah.
Okay.
So probably if we combine the 3 channels to which we can reach 2 sigmas, which would reach similar values as those 3 quotes, maybe.
I see. Okay.
For kappa 3 for 1?
In the
This.
Higgs assumes that kappa 3 is equal 1.
So this is on.
I don't know. I think the results for the. I mean, there are 3 channels giving 2 sigmas on the start point. That has been shown. Now in this setup, with kappa 3 being fixed and kappa 4 being allowed to vary, I don't know. But in principle, we would combine them to get better information.
Yeah, actually, this plot basically, I mean, say because the two plots are different in the sense that in one case the B tagging efficiency is 80%, 60%. So the idea is basically that you have more observables, and to get basically best information, you just basically combine them. So like actually the trilinear or the single Higgs case, in the double Higgs case also, what we have basically a complementary information. Okay, so that's the message. Okay, I can take questions now.